Okay, so the next topic is about the mesoscale wave generation and maintenance. Okay, this will be quick. This one is not, there's no equations. Okay, yeah, no equations. That's good news, right? Good news. Okay, so this so will be quick and just give you ideas of what's going on. Okay, and it's important in a way because sometimes when you hear some terminologies, okay, this will help you. Oh, okay, I have done this, and then that will help you to go to some papers or references. Then you can pick out, okay, more information. Okay, so the wave generation mechanisms, you have different kind of mechanisms which can generate or initiate the waves. Okay, of course there are different kind of waves, so there are different kind of mechanisms. And for example, the most common ones are like especially orography. Okay, that's mountain. Okay, yeah, orography. Everybody knows that word, right? Orography. Yeah. And then surface heating or cooling. Okay, and like at night, okay, or in the morning, okay. Okay, when you're heating at night, when you're cooling, that can generate wave too. Especially when the heating or cooling is associated with a mountain, then you can have great waves generated. And density current, as you know, that or density impulses that can also induce the great wave. And moisture convection, okay. And I'm going to give some examples. And then mesoscale instabilities, and geosophic adjustment, and nonlinear interruptions, okay. And also plus probably other mechanisms, not limited to those mechanisms. Okay. Orography, okay, we are going to talk about it, so I'm not going to spend time on this, okay. And the mesoscale great waves generated by orography is normally we just call mountain waves. Okay, so mountain waves is okay under this big category of great waves. Okay, mountain waves are great waves, but specifically generated by mountains. And density impulses. Okay, density impulses, okay, that can include propagating density currents, okay, like under thunderstorm. So say if we have a thunderstorm like this, okay, and because of evaporative cooling, that will produce colder air, and then colder air produce higher pressure. And then the pressure difference, the pressure gradient force will kind of help to propagate, okay, push this cold air against the warm air here, okay. So then that can trigger a new convection, okay, convection. And this convection can grow and merge with this. Or, okay, if they merge, then this thunderstorm will become, okay, larger and larger, stronger and stronger. But sometimes if this density current is pushing stronger, okay, against the environment flow, then you could have this individual generated, but they don't merge together because it's pushed so fast. And then that we call multi-shear storm. Okay. Okay, anyway, so this density current, okay, that can generate the gravity waves. And hydraulic jumps also can do that. Okay. And gas front, okay, can do that too. Okay. And this part of the front is called gas front. And this whole thing moving forward, right, is called density current. Here's density current. Okay, and this one is a strong contrast between warmer air and the cold air. It's called front. But this front is different from, as you know, different from the synaptic front. So we call the gas front. Okay, and sea breeze. Sea breeze also have the, okay, cold air push against warm air, okay, from the ocean toward land. And that the front part is called sea breeze front, and that can generate the gravity waves. And dry lines, okay. How many people know about dry lines? You know dry line? Yeah. What's a dry line? The strong moist contrast, right? And that normally, okay, it can happen in other places too, but its very famous place is in southern Great Plains in the States. Okay, like Oklahoma, like the Texas, okay, and there you have the density, like the okay, this Gulf of Mexico, okay, and so here, okay, Texas, the eastern Texas and western Texas, the air properties are very different, okay, so you, so you have probably Rockies like this, okay, Rocky Mountains. So here you have kind of dry air here, or moisture here, air here, okay, because of the Gulf, okay, of Gulf, and dry air from the desert. Okay, so the Arizona, Texas is very dry, and then they form a boundary, okay, which has strong moist on the eastern side, and the western side is very dry. And this called dry line, and that dry line can induce thunderstorms, okay, supercell thunderstorms, and that can induce the tornadoes. Okay, and so you have dry and very hot air here, and here you have moist and okay, kind of warm air here, and there's other air coming down from the north. Okay, that's cooler. Okay, so that's three origins of the air come together that give very complicated weather there, and that is the main source of the tornado, supercell thunderstorm. Okay, and you know supercell thunderstorms, right? Okay, what's the difference of supercell thunderstorms and okay, regular thunderstorms? Can rotate, yeah, can rotate. Okay, yeah, that can rotate, and that rotation, if you have heating, that will stretch the air, and then rotation will get stronger because of stretching term in the vorticity. Okay, when you're stretching, okay, the rotation will become stronger. So eventually it will be very, very focused, very strong rotation, and that will induce the tornado. Okay, so those can also, those kind of propagating mesoscale front and dry lines, sheet bridge front, gas front, and hydraulic jump. All those can induce the greater wave. Any question? Oh, it's because you have moist air and the dry air, okay, here. And so what happens is you have, when you have this dry line. Dry line in a way is like a front, but it's specific because front is defined as when you have control, strong control temperature. Okay, so you got front. Okay, and then winds here. Okay, and moisture too. Okay, but here is specifically, okay, big difference of moisture. And so when you have moisture difference, okay, then you have dry air. Dry air is hotter, right? So dry air, you push against this this moist air, is going to be lifted. Okay, it will be lifted. Right, just like a synaptic front. When synaptic front is pushing, and then air in front of it is going to be lifted, and then you form the thunderstorm. And you have dino thunderstorms like score line, right? Okay, so you have a synaptic front like this. It's similar to that. Okay, it's just a little bit different characteristic. So here it's pushing this way. So if you put yourself, okay, right in with the cold front, then the air, so you do like this, the cross section like this, A and B, A and B. Then this is cold air, right? Cold front. Then when it's pushing, this is okay being forced up. Okay, and then you can have thunderstorm form. Okay, and since the nuclear front, the synaptic front, okay, can extend for 1,000 parameters. So then you have many thunderstorms formed, and then in front of it, so this is we call score line. Score line also can induce mesoscale greater wave too. Okay, like this one. This is, you can see, okay, so you can see this is vertical motion, upward motion, that's just in front of the density current here. And this is very cold air, okay, compared to here. And then air is going to push it up and form the thunderstorm. Okay, and you can see this, those are greater waves. Okay, those are greater waves. Okay, greater waves. So you imagine when you're air, okay, so say you put yourself in the moon frame with the gas front here, then air is going to push up, okay, and generate waves, and you can see the wave tilting. See that? Wave tilting. Okay, those are greater waves. See here, those greater waves. So say if you probably can do an experiment now. Okay, a lot of people, a lot of students can learn the model. You can just put a mountain here. And I remember in probably 1990s, I went to meetings like a severe local storm conference, national conference in U.S. And I saw a poster and listened to talks about the multi-shear storms, okay, and they try to understand the mechanism, the generation mechanism, because they're super shear, they have kind of thunderstorms, okay, kind of mesoscale shears generated one by one, okay. So then I got the idea. I say, well, I think that is just like mountain. Okay, so then I put a mountain there. I can generate multi-shear storm. Okay, and actually that I published a paper there in, I forgot the year, but you probably can find it from my website. If you click on publication, and you can find it probably in 1998, Dean et al. Okay, that. Okay, so here actually, if you put a mountain here, you probably can generate some kind of wave like this, very similar. Okay, probably not exactly because they are not mountain exactly. Okay, but a lot of air cannot penetrate through very cold air. Okay, so they've been forced out and then generate wave. Okay, moisture convection can generate great waves too. There's something wrong here, something missing here, I think. There must be a figure here. Oh, here, okay, some photo here. So here is a simulation, ideal simulation of a thunderstorm, and you can see this upward motion here, and there are lots of shears. Okay. Kind of strong, okay, shears. Within a thunderstorm, it's not everything is going up. Okay, in between some air going down, so you have kind of convective shears. Those convective shears, those convective shears, see here, those convective shears can generate great waves. Okay, propagate upward. See that? And this is in the beginning. Later on, the thunderstorm become larger, stronger, and now you can see very well organized great waves generated. Okay, see here, first tilt, okay, they represent the great waves. The wave energies are being pushed, propagate upward. Okay, so. And then this is another example. This is from one of my earlier papers, 1988 paper, which I think I probably have shown you this figure. Okay, so this is generated by score lines in this region. Okay, in this region, and then that generated and propagate to the Boston more than 10 hours. Okay. This wave, this is a specific wave. We call it solitary wave. And geostrophic adjustment, okay, can also generate waves too. Okay, like this is favorable region for wave activity. Okay, and those the low pressure and cold front, warm front, okay, and they can interact, and then they can generate great waves here. Okay, this type of great waves are larger great waves. Okay, looks like a meso alpha, like 700 kilometers. Okay, in wave length. Okay, this is one of my papers I published with a PhD student at NC State before. Okay, it's kind of linear theory. Okay, we can generate waves out. Okay, outward like this, outward like this, outward. Okay, and this is generated by a jet. We impose a jet there. Okay, a mesoscale jet. Okay, like a jet like this, and then that can trigger waves propagate outward as well as upward. Non-linear introduction also can do that. Okay, so next thing is try to introduce you about the wave maintenance mechanisms. Okay, because wave can be generated, but great waves, a lot of them are dispersive. Okay, and so they are easy to just disperse, and then you don't see it. Okay, but some of them can get organized and propagate for longer time. Okay, so here we are particularly interested in those great waves which were produced and also can propagate for a long time. Okay, so then you are curious about what's the maintenance mechanism. Okay, just like hurricanes, okay, typhoons, okay, why they can sustain so long. Okay, so you need some mechanism to maintain the system. Okay, here, based on the observations, analysis, and we can get organized for those longevity. This called longevity of these long-lived large amplitude mesoscale waves. Okay, one is wave ducting mechanism. Okay, so when you see that wave ducting mechanism, okay, then what we did in previous chapter, like wave reflection, can be applied to there. Okay, wave ducting mechanism, and then cyclic wave mechanism, and then wave disk mechanism. Okay, and this also can help you when you are reading some literature papers. Okay, can help you to understand. Okay, first is wave ducting mechanism. Okay, and Linson and Tang, 1976, in 1970, they proposed a kind of conceptual model. Okay, try to explain the long-lived mesoscale waves because they are theoreticians. Okay, as you know, probably Linson is a theoretician, and Tang is his probably PhD student. Of course, right now he is a professor at University of Washington. And Linson and Tang, they propose a mechanism. They based on the observations. Like they are not doing observation analysis, but they based on what people found after observation analysis. Then they come up with the conceptual model. Like, okay, here you have this stable layer, and you have this stable layer, and you have convective unstable layer. Okay, layer here. Okay, and then here also have the critical level. Okay, so what we did, okay, can be applied here. Okay, now you know what the characteristic of critical level, and you know what could cause the wave reflection. Okay, and here you have the temperature inversion. Okay, so then they idealized into this. Okay, based on those observations, okay, concept, okay, and then they organized, they kind of built up a theory. It's a theory, linear theory, and based on that above, then they say, oh, okay, you have this kind of structure of the basic wind. Okay, so your basic wind, okay, flowing this way and then flowing this way. Okay. You may have some kind of question about why in low level you have air blowing this way, upper level blowing this way, because normally you don't see that kind of structure of the wind. Okay, the thing here, the key here is this: the key here is you have to put yourself into the moving frame of reference. Okay, yeah, so say if you have a thunderstorm, okay, and so say this thunderstorm is propagating at this speed, and then if this thunderstorm is embedded in a in a basic wind like this. A basic wind like this. Okay, it's moving at this speed, say c. Okay, and this is U of G, the basic wind. Then, okay, then if you put yourself in the moving frame with a thunderstorm, then this is C. Then this height is called what? This level is called what? Critical level. Okay. And then if you put yourself into the moving frame, then what happens is you are going to see, you are going to because you are moving, okay, with a thunderstorm. So if you are moving with thunderstorm, you see on top, the wind is blowing to the right, and in the door there, blowing to the left. Okay, that's what they have in mind. Okay, so basically, the wind is is blowing in a lot of cases are blowing same direction. But if you put yourself in the moving frame, then you see on top, wind go this way, and the bottom you go this way, and then the wind reversal here. Okay, the wind reversal here is critical level. Okay, when you put yourself in the moving frame. Okay, that's why we have this one. Okay, so in that case, okay, we have this kind of wind structure. In that case, we have this kind of wind structure. We have weaker wind here, like this. This is a basic wind. This is U of G. Okay, now, if your system is moving at a speed like this, okay, this is C, okay, then this is critical level. Okay, you do move speed C, then this is critical level, and then what you see is like this. You see wind go this way, blowing this way, blowing this way. You see wind blowing this way, this way, this way. Okay, and then you have three layers. Okay, one layer, you have uniform wind blowing to the left, and then you have wind here, you have uniform wind blowing to the right. When you put yourself in the moving frame with the system. Okay, that system could be the wave, could be thunderstorm. Okay. So here is a wave. Okay, that is so important this way, and then they solve the linear problem. Okay, and then they found. Okay, so see here also they have structure of the N2, N3, N1. Okay, so here it's stable, there it's stable there, this is unstable there, or this is stable there, okay, N2. Because N2 is less than N3. So when your N differences, you could have existence of wave diffraction, like we just learned, okay, before. Okay. So let me, give you a quiz. Let me ask. So you look at this, and you don't look at the note. Okay, just try to memorize. Try to kind of try to recorrect your memory. Okay, from what we learned yesterday. So which layer could have the wave kind of being reflected back and forth, up and down? Which layer? See here is stable, right? This base is stable, right? So if your omega is like this, right? Then you could have wave diffracted, right? You could have wave diffracted, which there, probably this there, right? Right? Because this one is greater than omega. And then that buoyancy force is stronger, so you can generate wave propagate upward. But here is evolution, so that will be, okay. Okay, so wave energy produced here cannot propagate upward. Okay, so a different kind of structure, you can different kind of wave diffraction properties. Okay, so you can have the and so then your wave could be kind of ducted here. Also, this is critical level. So, in case you have part of the wave energy propagate up here, will be absorbed by critical level. So a lot of wave energy will be trapped here, and that's called the wave duct. Okay, this is called wave duct. Okay, the low level is called wave duct. Okay, waves kind of trapped here. Okay, and the other mechanism is a cyclical wave mechanism, like this. Okay, you have seen this one. This one I try to explain when you had nonlinear. Okay, nonlinear effect. Then this one, just imagine. Okay, just imagine this one is like a shallow water wave. Okay, and it's deeper, right? So we have stronger wind flow. Okay, flow will be, okay, the first speed will be larger, and here is smaller, here is shallower. Okay, because C, the shallow water wave is equals to G times H. So if H, that's this depth of the fluid. So this is faster, non faster. So then it's going to have wave steepening, wave overturning. Okay. After wave overturning, of course, then you have the, because you have the core air or core fluid on top of the warmer one. So then it's going to overturn and then got the, okay, you got upside down, you get turbulence. Okay, and then you got turbulence mixing. Okay, now you look at this figure. You imagine this figure. So here, you look at the wave here, look at wave here. So say if we roughly, okay, this is just imagine, okay, roughly separate this as two parts, okay, here, okay, and look at, say you had wave here, you have wave here. So what's the wave length? Which one is longer, which one is shorter? You look at the front part and look, okay, and rear part, because waves propagate to the right, right? So you look at front part. The wave here has shorter or longer wavelength compared to here. Shorter, right? Shorter here, right? Shorter here. Here, wave is longer, right? Here, wave is longer, right? Here, wave is shorter. Okay, the wave is no longer symmetric. Okay, if symmetric, wave here, it has same wavelength in the front. So this, in a way, you can imagine this looks like it's it looks like you have your wave like this. Eventually, you look at this. So here is shorter wave, and here is longer wave. So this kind of wave steepening actually more or less looks like the shorter waves is propagate faster and leave the longer wave behind. Okay. And this is from the nonlinear effect. And then if you look at a wave governed by partial U, partial T, plus partial cubic, partial F cubic equals 0. So say we have C here, C here. Okay, maybe not C. Okay, maybe I just simply say maybe alpha, like this. And you can derive the dispersion duration. Right. What's the dispersion duration? So U will be equal to U hat. Okay, e to the I kx, right, minus omega t. This is only 1D problem, so it will be like this. So actually we can just say U naught. Okay. So what's this? Partial t will give us what? Right. And how about this? How about this? This will give us alpha I k cubic. Right. Okay, you have U naught here. You have U naught here plus equals 0, but U naught cancel out. Okay, because U naught is non-zero. If U naught 0, you don't have to worry about this because there's no problem. Okay, because we assume U naught is non-zero. So you divide by U naught, then you will get minus omega. Okay, and what's this? Minus I omega, negative I omega, and what's this? I to the cubic. Negative I times alpha times k cubic equals 0. Okay, so I cancel out, omega equals to alpha k cubic. So what's the C? The phase speed. Omega divided by k, very good. Okay, omega divided by k, that's equals to what? Alpha k squared. So what does this mean? So say if you have different k, okay, because k represents the wave number, right? And wave number is 2 pi over L, right? Okay, so for for larger k, what happened to C? Larger, right? No. Agree? Larger C, right? No secret. Okay, larger k, larger, okay. Okay, and smaller k gives you smaller C, right? Okay, so larger k means larger k means shorter wave. Okay, shorter wave is going to propagate faster, and then this is not quite right. It's not quite right. Huh? Negative alpha. Negative alpha. Yeah, you sure? Oh yeah, right. Yeah. Okay, negative alpha. So this means shorter wave. Okay, because the negative alpha will be travel. Okay, travel kind of slower. So that means your shorter wave will be left behind. Okay, so your wave for this on this, okay, your wave is going to have shorter wave deep behind. Okay, this because of dispersion. Dispersive effect, okay, dispersive effect. Okay, dispersive effect. So, under certain conditions, this is making the shorter wave moving faster, this leaving the shorter wave deep behind. These two effects can balance each other. Then that makes that wave, okay, because trying to steepen and try to leave, okay, shorter wave behind. When steepen means shorter wave, okay, going faster, these two imbalance, and that's called salutary wave. Okay, and that can last for a long time. Okay, and that was found by a scientist, the British scientist called Russell, when he was riding the horse, and there's a canal in her. There's a canal. Okay, and he sees a wave bump, and he was curious because that wave bump, okay, is propagate against the flow. Okay, the river go this way, and that bump, that hump of the water, propagate against it. So he kind of riding the horse, follow that. He followed 1 mile, okay, and then eventually dissipate, but it can last for a long time. That's called tidal wave. And this has been worked some time ago in 1800, okay, by Korteweg and DeVries, okay, 1895, okay, and Benjamin in 1936, okay, and they solved the classical, it's called KTV tidal wave equation, and then Benjamin also extended, and then because this assumes shallow water, and then for deep water, then you have deep water tidal wave by Benjamin, okay, and when that happens, that can last a long time. So look at here. So here is, which country is this? Australia. Okay, you guys are very smart. Oh, actually, you don't have to be smart because it's there, right? Okay, it's literally there. Okay, so here, there's a cape, there's a mountain here, there's a mountain range here, and that in the morning, because of cold air, built up at night over the mountain, okay, because of radiation. And then you can have cloud coming down, and lying cloud, okay, like this, coming down over the from the mountain, and then propagate over the ocean. And that is happened. That kind of cloud is like this, cloud line, almost two-dimensional, and many of them, and then propagate. And that's happened in the morning, so they call morning glory. Okay, glory is one type of cloud, okay, kind of blossom in the morning, okay, morning glory. So that happened in Australia. And later, okay, they have other cases like that. And then American scientists, they say, how come we don't have this kind of morning glory? And actually they found it, okay, over the Oklahoma. They found also similar phenomena, just not as often as Australian cases. Try to find it. Try to find it, okay, yeah. Now try to find it, but probably not, okay. Probably not. You need a certain conditions. I think Towns Mountain is probably a little bit too high and also too long. This is kind of relatively, okay, smaller. And so if you go to that KTV equation, okay, and you can see here, this is local rate of change with time, right? And this is advection, right, term. And this is what this term. What's the physical meaning of this term? What's this term? Downlink effect. So this term makes shorter wave propagate faster. This is dispersion, third order, okay, dispersion that makes shorter wave left behind. So these two, okay, could have imbalanced Not always, but under certain conditions, it could be imbalanced. Okay, so then you can solve that equation. And Kennedy equation is one of the very, very few nonlinear equations which you can solve analytically. Okay, that's one of them. Okay, yeah. I think the Burger's equation also you can solve it. And then I think in physics there's another one, very famous one, I forgot the name. Okay, also you can solve it, but not many. Okay, so this is one of them. Oh, also later we're gonna learn it, like Dong's equation is also we can solve it. It's nonlinear. Okay, but in linear form, so you can solve it. So this you can solve it. So you can solve it is in hyperbolic secant. Okay, function. Okay. This is hyperbolic secant, okay, function. You can solve it, and then you can get this, okay. And so when they are exactly in balance, that's called sided wave, only one wave. But when it's developing, okay, and then they can split into different sided waves, and each one is in balance. Each one is balanced, and those are called solitons. Okay, solitons. Okay, so that's a second mechanism which can make. So I also have applied this kind of theory to explain that Dean and Gauss paper. Okay, and then later on other. Okay, this is from Dean and the Gauss. Okay. Paper, okay, and then this figure is produced by other scientists, Rotman and Einauti. Okay, they extend that study to use this to explain. Okay, and then next thing is the wave shift mechanism. Okay, so for the wave, mesoscale wave, to maintain long-term propagation. Okay, three major mechanisms have been proposed. One is wave ducting. So when you have structured atmosphere, that means your Brown-Wessel frequency can change with height under certain conditions, certain structure. Then the wave could be, energy could be trapped, cannot propagate upward, okay, or trapped in a layer, and okay, and then that can help to last long time. And other one is I just mentioned, like Kennedy equation, this sided wave mechanism that can also help. And other one is wave shift mechanism, and which I think we can talk about it after the break. Okay, let's take a 10-minute break. Okay, thanks. Of wave number, also function of wave length. Okay, so what does this mean is, okay, the wave speed is proportional to the wave length, because this is function of 2 pi over L. That's function of L. Okay, so it's wavelength. And then remember I sketched that a family of 4, okay, the father, mother, okay, 2 kids, okay. If people are working at different speed, then the wave pattern will be distorted and looks like dissipating. It's not dissipating, okay. It is dispersion, okay. So this kind of shorter wave moving ahead of the wave and shorter wave behind the, okay, by 2 different effects, they could be imbalanced, okay. A longer wave behind, longer wave propagate faster, this could be imbalanced, and then that wave can last for a long time, okay. Of course, it cannot be forever because, okay, we also have to consider the dissipating effect, okay, dissipation effect. We also have to consider that, okay, and then that will make it gradually dissipate. But these 2 effects can be imbalanced. Any questions about this? Okay. Yeah. Okay. Okay. So now, next mechanism is called the wave shift mechanism. Okay, and the wave shift mechanism is they borrow the idea of shift mechanism. Okay, and to explain the, okay, wave can maintain for a long time. Okay, and how many of you are aware of shift mechanism? What's shift? Typhoon, hurricanes, okay, tropical cyclones. Okay, so shift mechanism is used to explain the generation and maintenance of the tropical cyclones. Okay, that's from the, okay, tropical cyclone. Okay, and of course, some of you probably are aware of, okay, there are new theories coming up, and because the shift cannot totally explain the generation and the maintenance of tropical cyclones, so it's become not popular now. Okay, so you have to be aware of that, and the main reason is because it's based on linear theory, and that predicted the scale of the favorable growth of the tropical cyclones is not consistent with the observations. Okay, so then you got the wish mechanism, like Emmanuel's wish mechanism, and then there are newer mechanisms proposed. Okay, but that's not our topic. Our topic here is to borrow the idea of the shift to explain this. And so then shift mechanism is like this. Okay, so so the shift stands for the convective. Sorry, not convective. Conditional instability. Okay, of the second kind. Okay, so what happens is when you have a conveyor system. So you have a conveyor system here. Okay, you need strong upward motion. Okay, conveyor system need strong upward motion, and you need that will trigger the latent heating. Okay, so trigger strong upward motion, and but in the beginning you need what? you need convergence. Okay, so in a convergence, like this. So in a convergence, and trigger upward motion, and then you got heating. Okay, so your W. Okay, and then here your convergence. Okay, so convergence, trigger upward motion, and then trigger even stronger upward motion because of latent heating. Okay, and then you got outflow. You got outflow, and this will generate second generation coming back in, and then because of boundary layer, okay, boundary layer friction. So here boundary layer friction that help to get convergence. So then you got self-sustaining system. Okay, so here PBL friction. Okay, that's add up to convergence. So in the beginning, you have convergence. Okay, and then you got upward motion, and then you go up to LCL. Right? Oh, I have it here. Okay, so. Okay. Hello? Okay, so, okay, you got latent heating, right? Because above LCL, got latent heating, and you have to be above LFC, okay, the level of free convection, and then you got, okay, lateral release of latent heat and that's strong, and then you produce, okay, outflow on top, and then coming down. Of course, this is all rotating, okay, and then coming down, and then flow comes in, and with a help from the PBL, the planetary boundary layer friction, and then get the convergence stronger, and then kind of become self-sustaining system like this. Okay, so this is called CISC. Okay, we call CISC mechanism like this. Okay, now why we are talking about CISC? Because we are not talking about tropical cyclones. Okay, we are talking about the mesoscale waves. Okay, why is we borrow the idea. Okay, same thing. You have convergence, you have upward motion, and then you produce outflow, and then you produce secondary circulation. Okay, now the convergence part is not helped by PBL convergence friction. It's instead it is caused by wave. Okay, by wave. So that convergence part, okay, if it's replaced by wave, if this part is replaced, okay, by wave induced convergence instead of boundary layer. Okay, so you can have the totally enriched flow, no friction. You can still have this, and this is okay. It replaced, okay, replaced by CISC-induced convergence. Then this mechanism is called wave CISC. Okay, yeah. And so now, if say you have a thunderstorm here, okay, so everybody got this? Yes, yeah, okay. This part, okay, so I leave that part off. So actually I can use that. Okay, and also there's another one here. Okay, you have very good facility. You guys are lucky, yeah. Okay, very good facility, yeah. So if we have a thunderstorm like this, okay, we have heating, okay, and generate it like this. So, okay, you can idealize the convection like this. You can look at this now. Tell me, what is the air motion here? What's the air motion here? We have upward motion, right? Go up. So when the upward motion go up like that way, that is equivalent to you move the mass. Okay, you move the mass up to here. Okay, so in a way here, the mass will be accumulated. Okay, in other words, your mass is going to increase, and here mass is going to decrease, right? Because you move a mass to there. Okay, so in some theoretical studies, okay, they can rewrite the equations. So then instead of heating, they put a mass. Okay, so I have mass source here and mass sink here. Mass source here, mass sink here. So then you represent upward motion there, like a thunderstorm. Okay, so in some theoretical study, they do this. Okay, so instead of use Q, they use mass source and sink. And do you know what the reason they want to do that? Okay, these days people no longer do that. Okay, why they do that? Because it's because of theoretical study. And when you have theoretical study, you have some of them, they study hurricanes. Okay, and they use shallow water equations model to do it. But shallow water model doesn't have heating term. Okay, doesn't have heating. So that heating cooling couple is representing the heating effect. Okay, that's the reason. Okay, so now that's why they put a mass source there, mass source, because you accumulate mass there. Okay, that's thunderstorm center, and that can generate a wave. Okay, like this, generate wave, and the wave propagate out like that. Okay, and so that is kind of based on this is based on the Oasis model of. Okay. Okay. Of the Raymond's 1983 paper based on that. Okay. Okay. It is also in my book. Okay, I review it. Okay. And now think about this. Think about this. So this is a better conceptual model of the thunderstorm. Okay, of the thunderstorm. So they cannot hear us. They cannot see us. Oh, it doesn't move. Move too fast. Huh? Maybe out of battery. This is power, right? Oh, maybe because of this. Yeah. Maybe out of battery. Yeah. I remember he mentioned to me there's battery here. Okay, yeah, you just that. Okay, thanks. Yeah. When you're tired, you let him do it. Okay, so it's not working. Okay, so now this is a conceptual model of a thunderstorm. Okay, so you have upward motion. Okay, you have convective shears embedded in the whole thunderstorm. Okay, upward motion, and then you have downdraft because of flow associated with the precipitation. So you have rainfall here. Okay, and rainfall here will produce cold air and that push and produce a gust front, right? So when your gust front pushing this way, then here you have convergence, right? That's convergence here. And here, because cold air will spray out. Okay, cold air push this side, also push this side. So you have divergence here. Convergence here. Okay. Now think about this. This is very important. So when you have this system now, so a convergence here, right? So now, if the thunderstorm, okay, and this convergence, right, and then that can trigger wave. The wave can induce the secondary circulation come into here. Okay, right. Just thinking about this as a wave system. Then you got coming in here. Okay, so then this wave generated convergence. If the wave speed is same as or close enough with the propagation speed of this thunderstorm, then this is always been there. Understand? Been there. Don't understand? Maybe let me use a different way. So say you have a thunderstorm like this, okay, and precipitation, you've got gust front. Okay, so here you have convergence, okay, convergence here. Okay, now if this is propagate faster, okay, away from the thunderstorm. So say thunderstorm is moving at a certain speed c, and this one, so say c1, this one at the speed of c2. This thunderstorm is not going to maintain or grow. Why? Because your convergence is here, right? Your convergence here, okay, you got convergence shear here, and those shears, because they are moving faster, so those shears are spread away from this main one, so it's not going to develop and merge, become a stronger system. Okay, now if C1 is equals to C2, then it's going to maintain itself. Okay, and this convergence also part of it coming from the secondary circulation. Okay, so if this convergence is moving at the same speed as the gust front or the thunderstorm, then it's going to maintain itself. Okay, so just you just view the thunderstorm as a wave system. Okay, so that is called wave system. Okay, and that can help. Okay, so now you understand that. So now, okay, now come back to here. So say now, if this gas front is always moving same speed as the thunderstorm, you have convergence here. And now you have secondary circulation, that convergence is moving at same speed as thunderstorm. Then here is always have a convergence. Okay, and that's in phase with the propagation of the thunderstorm. And then you got continued supply of convergence, which can produce upward motion, and that can help maintain the system. That's called wave system. Oh, here. By the way, probably it's because out of battery. This one? Oh, okay. C2. Oh, it's when you have heavier precipitation, you got more evaporative cooling and stronger and more with it. And other thing is also, also the system here. Okay, sometimes some thunderstorms, they have the basic flow, they can be adverted. Okay, and so if their basic flow is weaker, then this can be go faster. If that wind is stronger, then that can catch up this. Okay, so that's about it for this part. And of course, there are more things, in-depth discussions, which I refer you to do it, I kind of cut and paste from my book, so you can do it if you're interested, So this will tell you how do you solve the problem, You use the method of separate variable, and then try to solve the KTV equation, and you can get it. And also you can apply it to deep water, Not only shallow water, you can also apply deep water, but they have different solutions, And that deep water cycle wave is called the Benjamin Davis Ono equation, BDO equation, and they have different solutions, And both of them, they have they're dispersive, Here is k to the third, and here is k squared, But both of them are kind of dispersive, So, and then you can have different solutions, So you can read it, and if you want details, you probably can also go to my book, which you can, you can borrow it from the library. There's a book, So I think it's chapter 4, chapter 4 of this book. So that's it for, this is a shorter chapter, I just want to give you the concept. So next thing is the mountain waves. Okay, so I changed a little bit of the table of contents. So I changed a little bit. Okay. So here I have the 7.1. If you copy down or you print out the earlier lecture note, okay, basically the same, but I just combine the. First I call it the two-dimensional flow over sinusoidal mountain, and then other chapter is sinusoidal. Other flow is flow over the isolation mountain, but I combine together. Okay, is okay, this part and then this part. Okay, so this one we'll talk about two-dimensional linear flow over mesoscale mountains. Okay, and then we'll talk about the governing equations again, and then talk about regimes of stratified flow over mesoscale mountains. Okay, and this part will be kind of sinusoidal mountains. Okay, I should change this to sinusoidal mountains, and here to isolation mountains, and then we are kind of varying the basic flow structure. Okay, not uniform flow. In other words, your capital U is no longer constant with height, and then we'll talk about what happened, and then we talk about trapped D waves. Like on this side, you have D waves. Okay, so first, let's talk about the governing equations. Well, this is supposed to be a little bit ahead of 7.1, supposed to be introduction. Okay, so many all-around weather phenomena are directly related to flow over mountains. Okay, and like mountain waves, D waves, and clouds, and daughters and the daughter clouds, and like a severe downslope windstorms. That's a very famous problem. Okay, and then also D vortices. On this side, you have a pair of vortices generated, and also you can have the kind of the vortex setting. Okay, the vortex generated and one by one generated and kind of being drifted, propagating downstream. And you can also have the frontal distortion across mountains. Okay, front passing through mountains. Okay, and this kind of distorted. Okay, like in Alps, like this. Alps is shaping like this. Okay, so front passing co-front, the synaptic front, passing through mountain, and then you find here it goes faster, and eventually they come together and generate cyclones. That's called decyclogenesis. Okay, yeah, and that happened in Taiwan too. Okay, in Taiwan too. In Taiwan too. Okay, so you have front. Is it Taiwan? Yeah, like banana. Okay, is Taiwan supposed to be hanji? Okay, like that hanji, right? Okay, like this. Yeah. Okay, so front. Okay, and then passing through. This side is going faster. Okay, and then eventually they come together. Okay, and this, from my point of view, okay, most of our scientists here in Taiwan, they tend to think this is because of southwesterly monsoon flow, kind of make it, okay, stop it moving that fast. But there's no southwesterly flow here. Okay, and the reason is because later we're going to learn. Normally, in the mountain region, you have high pressure generated. Okay, so this part will be pushed faster, and you have high pressure generated, and this part will be pushed faster. Okay, and of course, this one probably is combination of the high pressure here, and then also there's a southwesterly monsoon flow. Okay, combined together, so it's spread. Okay, in Taiwan's case. Okay, also you have the core damming, okay, and track diffraction of mean latitude and tropical cyclones. Okay, you can track diffraction. And coastally trapped disturbances and orographically induced rain and the fresh flooding. Okay, not only track, but also can enhance the rainfall when the cyclone passing through, like typhoons passing through, and orographically influenced storm tracks. Okay, most of these phenomena are mesoscale and are induced by stably stratified flow over orography. So understanding the basic dynamics associated with stably stratified flow over mountains is important. Okay, that can help us to improve the understanding of those phenomena. In addition, understanding that the dynamics of orographically forced flow will also help on different aspects of meteorology, such as turbulence, which affect aviation safety, wind damage risk assessment, pollution dispersion in complex terrain, okay, and subgrid scale parameterization of mountain wave drag, okay, in general, circulation models, okay. And like one example is like when I go to graduate study for PhD, okay, I went to South Dakota School of Mines and studied the cloud microphysics, okay, cloud modeling, okay. So I contributed to have a kind of relatively popular scheme like Dean et al, okay, microphysics, okay, parameterization. And then I went to Yale University for PhD. I focus on dynamics, no longer deal with microphysics. And so I studied mountain meteorology. But then later on, okay, because of mountain meteorology, I had to learn other phenomena. So then I was able to do some other problems too, not only mountains, okay. And so that is one example. If you learn well about the mountain meteorology, okay, the research, then you can do other things, okay. Okay, some fundamental properties of flow responses to orographic forcing can be understood by considering a two-dimensional steady state, very simple problem, okay. Adiabatic, inviscid, non-rotating, Boussinesq fluid flow. Sometimes you wonder, do we really have this kind of flow in the world, okay. Probably not, okay. But you take out some non-important things, okay, and this is still very useful, okay. Even so simple, okay. A lot of basic dynamics are kind of caught, okay, by this type of simple flow. Okay, now we go back to 2.2.14 to 2.2.18. How many people are on the watching here? 8. Okay, so this 8 is kind of reaching steady state. Okay, yeah. Yeah, always there, yeah. Yeah. If they are there, if they are not there, at least they didn't turn off the YouTube. Okay, so let's go back to 2.2.18, 14, and 2.2.18. Okay. So now it's 2D. It's 2D. So then, and it's non-rotating. So we can get rid of this equation, right? And it's 2D, so this is gone. Partial y is gone. Okay. And okay. Oh, we have homework like that, right? Do we do? Oh, okay. Yeah. So then you can reduce to a simple equation. Actually, we have done this before. Okay. So we reduce to this. Okay. And then those equations, okay, can be further reduced to the Scholar's equation. Okay, reduced to Scholar's equation like this. Okay, and this one is, you can write it out, is d square ds square plus d square dg square times w, okay, prime, right? 2D, so we only have partial x, partial y, partial g square, okay? Because that is Laplacian, okay? Laplacian is equals to this for 2D, okay? And then plus L square, G square, okay? So plus, okay, so we have L square of G that is defined as the following. Okay, so we have n square over u square, and then minus ugg times u. Okay, and then we have w prime equals to 0. Okay, and this term we define it as L square. Okay, L square. And remember, if there's no wind shear, okay, no vertical shear, or the basic flow, then this equation reduced to partial w prime x, partial x square plus d square w prime dg square plus n square over u square times w prime equals 0. And that is what we started in previous chapters. Okay, remember we had that. Okay, so yeah. Okay, so and this is called, this L is called Scholar, okay, parameter. Okay, L is called Scholar parameter. Okay, very important parameter in mountain waves. Okay, and so then, we are going to, we're going to look at this equation again, okay, in this afternoon, okay, and then we start to study the mountain wave theory, okay, the two-dimensional, okay, steady state flow, okay, because there's no partial t, steady state flow over mountain, and the difference is we have mountain forcing, and in previous chapters we don't have the mountain forcing. Okay. Yeah. Okay, so I'm going to stop here and let's take a lunch break. Okay. Yeah. So have a happy lunch. Okay. Okay. So let's start this afternoon's lectures. Okay, so when we consider steady state, two-dimensional, inviscid, Boussinesq, and non-rotating, okay, and fluid flow, then the also small perturbation, that means linear. Then these set of equations, okay, the original set of equations can be reduced to 5.1.1 to 5.1.4, okay. And these four equations, okay, as you know, the first one is the momentum equation in x direction, and then momentum equation in z direction, height direction, vertical direction, and then incompressible continuity equation, and then also we assume adiabatic, okay, and then so we have the thermodynamic energy equation. So those four equations can be combined together in terms of W prime, then that equation will become like this, okay, like this. And this is also called Scorer's equation. And Scorer's probably was the first one reduced to this form, and that we can write in this way. Okay, same thing, like 5.5, 5.1.5, except the Laplacians, okay, we kind of write out Laplacians. And L square is equals to n squared over u squared. This bar is called over, okay, UGG over u, okay, times W prime equals 0, okay. Okay, so in L square defined as n squared over u squared minus UGG over u is the scalar parameter square. Okay, so L is called scalar parameter. Okay, so equation 5.5.5, that's this equation, is a central tool for many theoretical studies based on that equation. Okay, and this equation also can be interpreted as a vorticity equation. Okay, a vorticity equation. Okay, and how do you interpret this as a vorticity equation? What we can do is multiply by u. So we multiply u. That gives us the following. Will be, okay, this will become W prime xx plus W prime gg, right? So you multiply it, then we got u times wxx prime plus wgg prime. Just different way to write it, except, okay, in this way we multiply u on all the terms, and then this becomes becomes n squared divided by u times W prime and minus u gg times W prime equals to 0. Okay. And this term is the rate of change of vorticity following a fluid particle. Okay. Understand? Anybody have problem with this term? Okay. The physical meaning of this term is the rate of change of vorticity following the fluid particle. Of vorticity. Okay. Anybody knows why? No? Okay. Let me give you a hint. Okay. So W prime of x, wx prime plus wg prime, what's this? What's that? I probably write it in a kind of unfamiliar way. If I write it in a way like continuity question, very good. Okay. Okay. So this means dw prime dg be equals to negative dw prime dx. Okay. So now this term is u d squared w prime dx squared plus u dw prime dg squared. Okay. And we substitute dw prime dg into here. Okay. Then this becomes u, okay, d squared w prime dx squared plus u dg of d w prime dx negative. Agree? And we swap this, bring negative out. Or maybe I keep it here, and then have negative dw prime dg here. Okay. And I bring one partial x out. Then that gives us, maybe I write down. You got this, I believe. Okay. This, okay.
I don't know why this equation is a continuity equation.
This is continuity question.
Continuity equation should be partial u prime partial x.
Oh, yeah, that's right. Right, that's right. Yeah, okay. So you're supposed to partial u, partial x. Right. Okay, that's very good. Okay. So I did it on purpose. Okay. Right. Yeah. So looks like some people is not okay, kind of sleeping. Okay. So this u prime dx. Okay. So then this become minus negative du dx. Agree? Right. Double check. Maybe it's not. You sure?
Yes.
You sure? Okay. You sure? Okay. I trust you. Okay. So now this become u. U prime and u prime. Now we are okay, right? Agree? Okay, good. So now you got this. Okay, so it's correct now. We can erase it. Okay, so this becomes, we bring one partial x out. We have u, right? We have u. Okay, so now we have u partial x. And then the then I write this first. Negative du dg. Maybe it's okay. Yeah, it's okay. So I have partial w prime, partial x, minus partial u prime, partial g. So getting clearer now, right? Okay, so if we have partial w partial x, so right, this is w prime. So if we have partial w prime, partial x, then we have multiplicity, right? Right, where vorticity? Right, go this way, this way. So this is which kind of vorticity? It's y vorticity in y direction. Okay, but this is negative y. Okay, negative y. Okay, so this is give us y vorticity equation. So let's probably say, okay, so this is negative, the partial w partial x will be equals to y vorticity equation. So this is y vorticity. Okay, and if we have u, if we have u and partial g, so u prime, so say you have u prime, then we have this into it, right? Vorticity, and this is y vorticity. So the y vorticity is equals to the u prime, the g. This is have the perturbation wind shear, okay, in g direction, right? So we can bring these two together. So our eta, the y vorticity, is equals to, these both terms can contribute to it. So it'll be partial u prime, partial g, minus partial w, partial x. Okay. So basically this is this term so this term actually equals to negative u ddx of partial u prime, partial g, minus partial w prime, partial x. But this is eta, y vorticity equation, y vorticity. So this is negative u partial x eta. Okay. And also keep in mind ddt of eta is equals to what? Partial eta, partial t, right? Plus u, partial eta, partial x. That's it, because we don't have basic vertical motion. Okay, we don't have w, the eta, dx. We don't have this because no basic, okay, w, okay, because w is equals to w prime. Remember that? U is equals to capital U plus u prime. Okay, so we don't have this term. And then this term is gone. Why? Why? We don't have this term. Hey, come on. Steady state, not stationary. Steady state. Because steady state. Okay. So this means u partial eta x is equals to d eta dt. Okay. That's the total rate of change, okay, following the motion. So this is equals to negative d eta dt. Okay, because ddt is equals to u ddx. Okay, for steady state, two-dimensional flow. Okay, so that's why we say it's rate of change of vorticity following the fluid. Following the fluid is total derivative. Okay, so don't overlook this simple equation that has dot meaning in it. Okay, so when you look at equation, don't be scared by it. Try to make friends with equations. Okay, if you're a girl, try to make boyfriends. Okay, you can have one more boyfriend. Okay, if it is equation. Okay, yeah, you don't want to have two boyfriends, but additional one is a equation. That's okay. Okay, it's allowed. And okay, for boys, you can have you can make girlfriends. Okay, with equations. Okay, of course, you don't want to have two girlfriends, right? Yeah, just you have two girlfriends or you have two boyfriends, just like when you are eating. Okay, you有两对碗 okay, 一个就是一个就是 okay, okay, 想不过无用 okay, too busy, okay, so, but okay, make friends, okay, with equations are good, okay, you are encouraged to do that. Okay, so now that's total rate of change following the motion of vorticity. And this vorticity is Y vorticity. Okay, Y vorticity. Okay, now we have second term here. Second term here. Second term is split into two. Okay, so now we are done with this one, right? We're done with this one. I'm making the blackboard, okay, very busy. So we are done with this one. We are done with this one. Okay, and now what's the meaning here? Why I say this is vorticity equation? If I say this equation is vorticity equation, that means every term has something to do with vorticity. Okay, so now why we say this? Okay, can somebody tell me what's the physical meaning? Just nothing to do. Don't talk about vorticity because I'm going to explain it. Okay, just look at this. What kind of force make this? Buoyancy force. Buoyancy force. Because okay, because n squared, and then what do we have? Divided by u, right? Divided by u, and then 30 prime. This is equals to, but n squared is equals to what? Buoyancy, frequency over theta, d theta, d g, right? Okay, so this equals to 1 over u, g theta, d theta, dg, 30 prime. Okay, and this is called buoyancy term because because the theta dg, okay, is maybe let me do this, because theta divided by the theta dg is the ddg is proportional to negative d rho dg. Agree? Okay. Agree. Okay. So when you have density varying, that means theta varying. That means density varying. Okay. Density varying. That means you have buoyancy force because density changes. Okay. When you lift up, okay, it changes density, and then that give you expansion, and then create denser fluid. right? Because expansion and become colder, okay? And colder, oh, where are my friends? Okay, everybody's, okay, staying so far away and then become colder, whoo, and then shrink, okay, kind of sink down, and then passing the original level, and then at low level, because it's stratified fluid, so okay, pressure is larger, so squeeze it, okay, so become, okay, very uneasy because it bump into each other very often, so become, okay, hot, okay, and become warmer and become lighter, and then shooting up, and this is called buoyancy oscillation, and the force is buoyancy force, okay, that's, so this term is buoyancy force, okay, we explained that before, this is buoyancy force. Buoyancy, probably I would say effect. Okay, the force is buoyancy force. Okay, effect. Okay, and that's because we have gravity. Okay, bring up and down because of change of the vorticity, density. Okay, so now why? Okay, so why this is related to why this effect related to because of that affect the vertical motion. So that is, so why it's related to vorticity? Why? I'll give you 2 points if you can answer that. Why? That's related to motion, right? Vertical motion. When you're vertical motion, you create, okay, it's due to buoyancy force. You have vertical oscillation. We call, okay, buoyancy oscillation, and that can create vorticity. So say if I have air parcel here, okay, I have fluid, right, and then here I have upward motion. That creates what? Okay. Y vorticity. Okay. So this creates a pair of Y vorticity. One is positive vorticity in Y. This is negative vorticity in Y. Okay. So this is okay. So here is positive Y vorticity. Okay. This is negative Y vorticity. Okay. So this is probably positive eta. This is negative eta. Okay. When you downward motion, and then you create a pair of vorticity, but just opposite to this. Okay. So that buoyancy force, okay, produce vorticity. Okay. So it's a rate of vorticity production. You produce it. Okay. When you have upward motion, you create. Okay. Remember I draw this figure. When you have a thunderstorm, we have upward motion here. Okay. And then here we create vorticity, and that gives us secondary circulation. Okay. So this is the rate of vorticity production by buoyancy force. And then negative UGG W prime. Okay, so negative UGG W prime. So how do you interpret this? Okay, now it's your turn. Okay, yeah, do it. do it. Okay. Yeah. And tell me what you find. Can you find why I say that? Okay. And oh, disappear. Okay. Yeah. So what's a physical meaning there? Try to play around with that term. Okay. Play a little bit. Okay. Well, I give you a hint. Okay, I give you a hint. Okay. Bring back. But try to write in a way, try to interpret what I said is. So when you look at equation, okay, you have to kind of try to make friends with the equation and try to interpret it. And later, once you understand it, you have a very deep understanding of the equations. And then that gives you a lot of physical meaning and help you to understand the equations and, okay, then understand the mechanism. So how do you interpret that?
I think kind of
Observation.
observation.
By W prime. Okay. So you just have to rewrite it, right? You just have to rewrite. That's very good. Okay, very good. So this one, you write this way: negative W prime, the square, u, the g square. Okay. And then you write W prime, the g of the u, the g. Okay, and what's the u dg? So this is x, this is g, torsion, and this is u. Right. So this is u, capital U. Okay. So this capital U, u of g. Okay, so what's the u dg? That's produce the vorticity, right? Yeah. That's way. You put the leaves here, and that will turn this way, and that is into what direction? So this gives you, okay, y vorticity, but that y vorticity is different from that y vorticity. Okay, this y vorticity is associated with basic flow. Okay, y vorticity, okay, of basic flow, associated with, I probably should say associated with basic flow. And then this is advection by perturbation wind, not advection by basic wind. Normally we talk about advection by basic wind, okay, but here is perturbation, okay, advection. So this is advection, okay, by W prime of, okay, eta vorticity associated with basic flow. Basic flow is U, okay. It's U. Okay. Or you can say advection of the basic flow shear, okay. But that shear actually is vorticity. Okay. So now if you look at this simple equation, and now you interpret this way, okay, then you have pretty good understanding of what's going on. Okay, so that's basically it's vorticity equation. Okay, basically this is vorticity equation. Okay, you just write in a way you cannot see it. Okay. Okay, so everybody okay? Okay, so this equation, like before, we can, look at the extreme cases. So I guess I can erase this, right? Okay. Okay, if extreme cases, okay, extreme cases. First, if n square is very small, it's very small. That means this term is very small. That means this term is much smaller than these other two terms. That means the vorticity production produced, okay, by buoyancy force is minimal, very small, okay, compared to other terms, okay, because this total rate of change, okay, or advection or the oil vorticity by U wind. This is advection of basic wind vorticity by W, okay, prime. So if this is very small, then of course this term will become. Then the equation, this equation will reduce to the following, or reduce to U WXX prime plus W GG prime, okay, and also we assume, okay, we also assume, okay, no wind shear, no wind shear, okay, or constant wind shear. Okay, that means UG is equal to 0 or UG is constant. Okay, and both of them gives us UGG. Both of them give us UGG equals to 0. Okay, so then in this extreme case, this term is almost 0. This term is almost 0. So the equation reduced to this one. Okay, and that is that reduced to the U, and then 30 prime 30x square plus U 30 prime 30 square 30 prime dg square equals to 0. Okay, we divide by U, and U is not 0. Okay, U is not 0. So, okay, we divide by U, then this becomes d square 30 prime dx square plus d square 30 prime dg square equals to 0, or we can write in this Laplacian equals to 0. And this is called what? We discussed this before. Okay, so now you bring back what you learned earlier. Okay, when we talk about pure gravity waves, we say this is what? This is representing the potential flow, okay, or irrotational flow. Okay, so this is extreme case. Okay, so that means the stratification is not very, it's almost zero, very small. Okay, so if stratification is very small, that means the fluid is like water. Like water. Okay, so with like water, that means, okay, your pressure is not, okay, like stratified fluid. Your stratified fluid, okay, then then when you bring the air parcel or fluid go up, then the environmental density is same, right? Because it's same density. Density is not changing. So you bring this air parcel or fluid, maybe fluid, okay, go up, it's same density. So you don't change, okay. You don't change density, right? Because it's same. You don't change density. So then you don't have the distorting force.
It's the same thing like
More or less like that, yeah, okay. Close to it, okay. Probably even stronger than that, okay. So you don't have buoyancy force. You don't have any force to bring it back. That's called distorting force. Okay, so then you don't have wave generated. And then in that case, we become this irrotational flow, okay, and or potential flow. Just like our friends in engineering school, they study, okay. They don't care about these great waves, and then you don't have great waves generated. Okay, that's called potential flow or irrotational flow. Okay, so we studied that in chapter 3, okay, the 3.5.22. See, chapter 3 of Dean 2007 book, okay. In our lecture note, that is probably chapter 4, okay, chapter 4. That pure great wave chapter. The buoyancy force is negligible in this extreme case. Okay, so now second part of this chapter we are going to do is to recognize the regimes of stratified flow over I probably should say the sinusoidal mountains. So you probably want to change your note if you print out, okay, these sinusoidal mountains. Okay, I guess I probably, let me see. So we are going to study this. So probably I kind of take a break now, and then for 10 minutes, and then we start this, okay. Rather than kind of start here and just a few minutes, and then we stop, okay. So we'll start from here for the next lecture, okay. Okay, now, first thing is trying to use very simple problem to help us to get more deep, in-depth understanding of the problem, okay, or the fundamental dynamics. So that's why, okay, to avoid some complications of mathematics, we just use sinusoidal wave, okay, and not wave, the mountain. Sinusoidal. So we assume mountain is sinusoidal. It could be cosine function. It could be sine function. So we just simply use sine function. Okay, so we assume we have a sinusoidal terrain that h of x equals to hm, and then sine kx. So that means we only have one k. So then our mountain is like this. Okay, and so from the mountain peak to mountain peak, that is the wavelength, and this wavelength is terrain wavelength. Okay, terrain wavelength like that. Okay, so k, okay, will be 2 pi divided by L. Okay, again we are talking about angular, okay, frequency, angular wavelength. Okay, wave number. Okay, so we have like this. Okay, so now first thing is what's the difference from what we studied before? Okay, the equation is same. Okay, only thing is now we have forcing, and this forcing is the terrain like this. Okay, so only thing very important is different from before is we have very clear low boundary, and this boundary is different before. Okay, before was flat. Okay, terrain. You coming in, okay, and then you can have disturbance, but at surface, the low boundary condition is what? What's the low boundary condition here? We used before. It's W prime equals to 0 at G equals to 0. Okay, so now we no longer have that case. Okay, and basically, no matter what kind of rigid boundary, basically, if we have rigid boundary here, we have rigid boundary here, right? The wall. Okay, basically, your boundary condition is this: your flow comes into here. Okay, you cannot penetrate into it. So the vertical component, perpendicular component of the wind at the rigid boundary will be 0. Okay, so here, if this is vertical plane, right? Vertical plane, so you can have W near the boundary here, but you cannot have U wind into it. U will be equal to 0 here. Okay, U will equal 0 here, and you can have V here. Okay, so flow comes in to here, will spread out, cannot penetrate. So you can have W, you can have U, but you can have V, you cannot U. Okay, so if this is if here, then also flow comes in, you cannot have V wind. V will be 0. Component. Okay, so say this is X and G plane. So this is V wind come to here will become 0, but you can have U and W. Okay, and down here too. Okay, down here you can have U. Say this is low boundary. Okay, so it's no mountain. Okay, so same principle. You have flow perpendicular to it will become 0. That's W will be equal to 0. Okay, and flow will spread out, so you can have U wind, you can have V wind, doesn't matter, but you cannot have perpendicular component of the wind. Okay, at the rigid boundary. Okay, so here, now we are okay here. Now, what's the boundary? So, assuming there's no viscosity, so it's invisible. Okay, that means no viscosity. No viscosity. So now you have you assume since no viscosity, so you assume your flow will be forced to follow the terrain. To follow the terrain. Okay, to follow the terrain. So your flow will be like this. This will be flow. Okay, this will be flow here, and here will be parallel. Okay, here will be parallel, and here will be like this, like this. This is your flow. Okay, so this flow has two components. Here U, here W. Okay, I'm talking about perturbation wind. Okay, and that has to be parallel to the mountain. So parallel to the mountain is what? This is, what's this? Mountain slope. So how do you express it mathematically for the mountain slope? Okay, so mountain slope. Okay, very good. So that is partial H, partial X. Okay, so that means what? W prime over U prime. That's the slope. The flow follows the terrain. That equals to dH, or maybe just simply say like this, dx. Right. Right. This is the slope of the flow must be equal to the slope of the terrain because it has to follow the terrain everywhere. That's the low boundary condition at. Okay, G equals to mountain, right? Mountain height, H of X. This is low boundary condition. Okay, so that means W will be equal to U dH dx at G equals to H of X. That's low boundary condition. Okay, now we are working on the linear problem. Okay, so this W is equals to 30 prime. Okay, we kind of write it in perturbation form. So U is equals to capital U plus U prime. Okay, and H is H. Okay, of course we are assuming, okay, kind of small amplitude. Okay, so now we have this become complicated now. 30 prime equals to U plus U prime dH dx. Okay. So, and then at G equals to H of X. Okay, so that's the low bound condition. So don't overlook. Anybody knows what's overlook? Don't 小看, okay? Don't overlook, okay? Don't overlook the low bound conditions. It's very complicated. Okay, it's very complicated. It's a nonlinear problem. Okay, nonlinear problem. Why? Because if U prime is large enough, then you cannot ignore it. Okay, so and then so this term become appreciable, become large, comparable to this capital U, and you cannot ignore it. Okay, so in order to simplify the problem, okay, we also we treat the governing equations. We ignore this one. So we assume, okay, so we assume, I guess I can get rid of this now. Maybe I can get rid of here. Okay, so now we have this. So we linearize the low bound condition. We have two nonlinearities. This one is one of the nonlinearity, okay, and other one is this one. Because you have to apply the low bound condition at that location. Okay. So there are two nonlinearity. So we try to simplify the linearize the low bound condition. Okay. So first one is assuming less than U. Okay. So then that gives us 30 prime equals to u partial h partial x. Okay. Okay. And second thing is we assume the mountain height is very small. It's small. Okay. So it becomes kind of linear mountain, very small mountain. Okay. So then the apply this at g equals to 0. Otherwise, don't overlook at that. Or otherwise, you cannot solve it linearly. Or you cannot solve it analytically. Okay, not that easy. Okay, you can solve it, but you have to use computer to iterate. Okay, apply it the mountain surface. You apply it. Okay, mountain surface. You cannot solve it. Okay, using your pencil or your pen. So we have linearize two part. This on the nonlinearity, other nonlinearity. Okay, so we apply it to g equals 0. So this is our linear low bound condition. Okay, and this is our terrain. Okay, this linear bound condition. So once we have that, then okay, we can try to solve it. Or other thing is when you assume there's no friction, and then the flow will be flow kind of freely around the terrain. That's called the it's called the free slip. Okay, free slip with no bound condition. And sometimes you see some wording like non no free no non-slip, no bound condition. No bound condition. Okay, you have non-slip, no bound condition. That means you have friction. So when you have friction, then you have friction. So mountain slope, you have friction. Okay, even in flat surface, your u always equal to 0. Okay, at the low boundary here, always equal to 0. You cannot have free slip, kind of freely going over. Okay, and then in that case it's more complicated. You have to use the model to solve it, because when you have boundary layer, okay, and as you know, boundary layer has two effects. What are they? What are the boundary layer effects? Have two effects. One is one is friction. In boundary layer is friction, so that has frictional effects on the atmosphere. And other one is heating or cooling. Okay, so that's boundary effect. So you have a boundary layer, then here your u, v, w at the boundary is 0. Okay, and then on top, then you can have flow. And that's called no slip boundary condition. I think it's probably called no slip boundary condition. No slip boundary condition. Okay, so two types. We are going to use this one. Okay. Okay, so now, we have this, we require the free particles to follow the terrain. Okay, so we have this, W over U equals to 30 prime over U plus U prime equals to dH dx. Okay, since we assume h is only function of x direction, so we have the dH dx. If h is three-dimensional, then we use partial h partial x. Okay, so for 2D, then we can have 30 prime equals to u dh dx. Okay, at g equals to 0. For 3D, then 30 prime is equals to what? U partial h partial x plus v partial h partial y at g equals 0. Okay. Yeah. You have three-dimensional flow. Okay. Okay, so we are done with that. Okay, so now for a small amplitude mountain, then we can apply at g equals 0, and also we can simplify, because small amplitude mountain means it's going to produce smaller perturbation in u. That's u prime, right? So u prime is much less than capital U, so we can ignore that u prime when it compares with capital U. And then that's why we can have this u here. Okay. And also that's why we can apply at g equal to 0 instead of on the mountain surface. Okay. Okay, so now once you have that, then then h is equals to hm. hm is mountain height. Okay, mountain height. Okay, it's mountain height. So when we have sinusoidal mountain, so this is hm. Okay, and this is L. Okay, and then k is equals to 2 pi divided by L. Okay, like that. Okay, so now we have h, and we have this. So that gives us 30 prime equals to u partial x of this h of x. Okay, that is hm times sine kx. So that gives us u times hm, and then ddx of sine kx. And sine kx, the differentiation of sine kx will be equals to cosine kx multiplied by k, right? So then we have u hm times k, and then cosine kx. Okay, so this is our low bound condition now. Combine the particular mountain geometry, and then okay, with this low bound condition, we got this. And this is for this sinusoidal mountain, we have this. And so this is applied at g equals to 0. Okay, so now we have low bound condition. Okay, so now we have this. And you can write this one as 30 prime of x, and then g 0. G 0 means g equals to 0. Okay, that's 5.1.11. Okay, so now we can start to solve it. Okay, and so the mountain is sinusoidal, and the disturbance will be also sinusoidal. Okay, yeah. 龙生龙，凤生凤. Okay, so you have this, right? So you assume the disturbance, okay, will be sine function or cosine function. Okay, in general, it's a combination of cosine and sine function because both of them are allowed. Okay. You don't anticipate your mountain is sine function, and then on top will be sine function. Okay, because you should allow cosine, because you could have shift of the phase. Cosine and sine has different phase. Okay, so but you should allow that. okay, because the phase could be shifted. In other words, when you have mountain height here, it's not necessarily your wave will be maximum here. Your wave, that peak could shift, and that is because of cosine. So you need to allow both cosine function and sine function. Okay, if you just allow sine function, then you can still get solution, but your solution is partial, not complete. Okay, so we need to have this. Okay. So so this is our low band condition now. We're down here, we're down here. Okay, so now at 30 prime of xg, okay, we have two parts. One is we call W1, okay, of g, and then cosine kx plus W2 of g, that is associated with the sine part, like this, okay. And then we can substitute this into the equation 5.1.5, that is WGG, okay, WG plus, let me see, what do we have? We have, okay, I think what we have is, we have partial x square plus partial square, partial g square, w prime, w prime. Okay, and then plus a square over u square, and then the square w prime, the g square. I think the x square. The x square. I believe that's correct. Okay, let me double check it. I believe that's correct. That's this equation, right? So here will be like this. Laplacian. Okay, that's Laplacian. Partial square, partial x square plus partial square, partial g square of w prime. And then we have L square. That's the scalar parameter. Okay, that's equals to n square over u square minus, okay, UGG divided by U. Okay, so here we assume no wind shear. The basic wind has no shear. Okay, so this is gone because we assume, okay, uniform. We call uniform flow. That means no shear. Okay, so UG is equal to 0. Okay, so it is. So then the L square of G becomes L square because constant. Then we got, we assume N and U are constant for this particular simple problem. So then we have this become N square or U square. So, okay, I'm correct. Okay, here. So then, oh, we don't have ddx square here. We don't have dd square x here. We don't have W prime. I remember we have that. Let me double check 5.5.1. I believe we have that square root, square there. Do we? Okay, so now we let's assume that prime equals to before we use W hat, right? Like this. And then e to the I kx minus omega t. Remember that? Okay, we have that. But okay, since it's time dependent, it's steady state, so we only have ik. Okay, we only have ik. So now we only have simple problem because okay, we only have ikx. Because we don't have omega equal 0. Because omega is corresponding to partial t, negative I, like that. So if this is steady state, partial t equals 0. Okay, so we have this. So then we can kind of transform into Euler number space. And partial x will be corresponding to what? Partial x. I k. Good. Okay, so here ik. So you have ik square, and then a W hat plus W hat GG. Okay, we keep this. Okay, and then plus n square over u square, and then W hat equals 0. I believe we should have xx here. That's why I kind of write xx here. I believe that's what we learned earlier. Okay, that's what we learned earlier for pure graded waves. Right? Yeah, we should have, but otherwise we cannot have k square here. Okay, so here is probably typo. It's a typo. Okay, it's kind of typo means okay, typographic error. Okay, so you have typo. We call it typo. Okay, that means okay, typographic error. That means you type, you mistyped something. We call typo. Okay, so that's why I kind of always write dx here. D square W prime dx square. Okay, and so now here we also have ik square equals to 0, like that. Okay, so then we have negative k square W hat plus W hat GG, okay, minus n square k square divided by u square. This, okay, and then that gives us the following: W square GG, okay, and then minus something wrong. Okay, and then minus n square over u square plus 1 k square, not correct. Okay, something wrong. Okay, equal 0. This is supposed to be plus. This is supposed to be negative. Okay, something wrong there. Let me see why. Parameter. It's a good thing of teaching is because if something wrong, once you teach it, you find it, okay, and then you can correct it. Yeah, that's a good thing of teaching. Let me double check on this.
I have a suggestion.
Yeah.
We can start here for them to practice the project 1.
Okay, yeah, let's do that. Yeah, let's do. Let me double check on this. Okay, I believe what I note, my comment is correct. Okay, but let me double check. Probably my note is not quite correct, but typo. Okay, yeah, we type too much these days. Type. So you guys, okay, kind of do this too much. Okay, type too much. Okay, so yeah, go ahead. Let me double check it. Okay, so.
So we stop here, right?
Yeah, we stop here, and then you, yeah. Do you want to? We are almost 50.
Yeah, only 5 minutes.
5 minutes.
Or then practice.
Yeah, probably, yeah. Okay. Yeah. So what Chiao suggested to is probably use a few more minutes to, probably still good because if you have questions, they can ask us. Okay, so try to practice that project 1. Okay, yeah, right now. And your questions you can ask. Because now you have everything now. Okay, you should be able to compile the program and
How about the format of that project?
format.
Yeah, the format.
You do it first, okay, and then let's worry about probably discuss the model, okay, yeah. So you try to, to run it, to produce results, and then we worry about how to write it, okay, yeah. Yes.
I think this growth is related to this equation, and this is equal to this equation. But they have this square term.
Right. Yeah, right. I think you're right. It's because here we have this term, right?
Yeah. But this we don't have this term, so this.
So this is correct. Yeah, looks like correct. Yeah.
It's all correct.
Yeah. So because the unit also doesn't check. Yeah. So it should be W prime. Yeah. W prime. Right. W prime. Right. Yeah. Okay. Yeah, because otherwise the unit doesn't check. Here we get meter per second, right? And then here we have meter square. So that gives us per meter per second. Yeah, you're right. It's because of that the partial U, partial X term. So I think this is correct. This is correct. Okay. Yeah. This is correct.